All right, everybody, this is lecture 32. Again, as I mentioned by email, I'm going to be pre recording this lecture. And so this is just going to be a continuation of our discussion on MASTAN2. And I'm going to center the latter part of the lecture regarding or on an example of a beam analysis. The main things I want to cover in that example are how to create custom sections, how to do member loads, and shear and moment diagrams, concentrated moments, basically everything that we didn't cover in the first example, so that between the two, you'll at least understand pretty much everything you need to know to do 2D linear elastic analysis. It's not everything that MASTAN can do, but for the purposes of CE312, it's certainly more than enough. That's the latter part of the lecture. For the first part of the lecture, I want to go back to the truss example, and I want to talk about some Excel tips and tricks that you can use to make the analysis of the data that you can get from MASTAN a lot more straightforward. And I'm going to use the class project sort of as a motivation for some of the tips and tricks that I'm going to show you. So let me actually pull up the lecture from the class project, and I want to just remind everybody of some things, and maybe it'll kind of jog our memories a little bit. So let me move my camera up here. Maybe that'll be good. Okay. So I want to just refresh everybody's memory. I'm going to go kind of quickly through this, and then we'll get to some Excel and some MASTAN here in a bit. So we had a project exercise. Maybe I'll move my camera over here. I'm just playing around with the camera today. Let's go through an example project exercise, and this is what we talked about in lecture 13. And so we said we were going to lay out a truss for a 60-foot span. It was 24 feet wide. We had put the 1,400 pounds per square foot load. And we had a series of limits that we were going to limit it to W12s made out of steel. The axial stress on each member is limited to 36 KSI. We limited the mid-span deflection to 2 inches, and we had a cost of steel of $1.40 a pound. We had done this in class, but one of the things that we had discussed in this step-by-step process, such as laying out the truss, tributary area, truss analysis, member selection, and then vertical deflection. The discussion in class didn't really discuss the software applications of this. It was sort of just assuming that either you were doing it by hand or that that stuff wasn't important. And I kind of want to discuss the software aspects of it today. And specifically, I want to focus on selecting members and then the iteration part, because there's some tricks that can make your life a lot easier. We had laid out this truss. This was the truss that we were going to do. And for our 2D analysis, this was the structure that we were going to analyze. So we had, in the example in class, we had said, okay, here's the pressure load, the bridge width, and we had talked about tributary area, and we had gotten a load to put on each joint. And then, we said we're not going to load the joints on the end. We're just going to load the joints in the middle on the bottom. Each joint's going to carry the same load. And we get this, okay? Now, in the in-class example, we said, okay, here's the loads, here's the reactions, and then here's the forces on the truss. And when we first talked about this, we said, well, we're talking about method of joints and method of sections. You all can determine this. And that's not to say you can't do that on your project. You're certainly welcome to. But we have MASTAN. That's sort of, one of the points of this project is to run the project, run the analysis in MASTAN. So I want to open MASTAN real quick, and I want to talk about this. So here's MASTAN. And what I'm going to do is I'm going to open a model that I've created. I put a model here on the desktop. We'll open this one right here. And so here's this truss in class. Okay, now a little bit about this model, what I've built so far, because I did a lot of work prior to starting the recording. So I've built the model. I've created the geometry. I've placed the nodes, placed the elements, placed the fixities. Each joint is seeing that downward load of 168 kips. And I've applied the materials, but I have not applied the sections. So that's why the members are still dotted. Okay. Now, in your project, one of the things that was a limit or a constraint on your project is that you must use a truss system that is statically determinate. In other words, I sub t had to be 0. Okay. One of the reasons for that is that as you start iterating your truss design and as you start changing the member selection, it does not affect the forces in the truss members. So it doesn't matter if any of these members are W12 by 14s or W12 by 96s or whatever. It doesn't matter. The forces and the members won't change because method of joints and method of sections on a determinate structure isn't affected by what the member's made out of. So for the purposes of getting the forces in the truss members for the purposes of calculations, we can just assign any section that we want. So what I'm going to do is I'm going to go to Properties, Define Section, and I'm just going to define a single section. So we'll go to the database and let's just use a W12 by 14. I'm just going to use the smallest W12. It's not really going to matter what we do at this point, although I do want to at least make a note that it is a W12 by 14 for a very specific reason. So let me hit Apply. And then we've got to attach those to the model. So we'll click Attach Section, click every member, and apply. Hit Cancel, and now every member's solid, indicating that all the properties are assigned. I've got a fully determinate model ready to go. So we'll hit Analysis, Static, First Order Elastic. Make sure we change this to a planar truss. Hit Apply, and boom, the model is run. Okay. Now, one of the things that we discussed in class is that you can go into the results, and we can go element forces, and we can click this member and get a force, this member and get a force, and so on and so forth. But it's not very efficient to sit there and just click the members one at a time and then query that data, or click them one at a time and then just type that data into Excel. That's very slow. Okay, so I want to show you how we can get the data in the trusses a little bit faster. So let me hit Cancel here, and I want to go to File and Create Report. So let's go to File, Create Report, and what we're going to do is we're going to get the data for the element results, and this isn't totally necessary, but you'll see where it's going to come into value here in a bit. There's this checkbox up here that says delimited by vertical bars. I'm going to check that, and I'm going to hit Apply. Okay, and so what that does is it generates a text report, and you can see every column is broken up by these vertical bars. That'll make the Excel part we're going to do here in a bit pretty easy. Okay, so I've got this report. What do I do with it? Okay, so the first thing I'm going to do is I'm going to save the text. I'm going to hit Save Text. I'm just going to put this on the desktop, and I've got a few reports here I've already done beforehand. Let's just call this Example Report. We'll hit Save. Okay, and if you go to the desktop, you will see we have this example report right here. Now, if I open this report, this is what the report looks like. It's just a text file. Okay, pretty straightforward. So what do I do with it? Okay, so let me move this over here. I'm going to open up an Excel file. That opened up here on my other monitor. So we'll open up an Excel file. And let's take this text and let's copy and paste it into Excel. Okay, so we've got this copy and pasted into Excel. What do I do with it? Okay, well, the problem is right now what's happening is, all of the data is contained just in the A column because Excel doesn't know that these are each individual values that should go into cells. It's just thinking of it as raw text. I need to take this text and put it into columns. And I think most of you have done this in other courses. But if you haven't, it's a pretty straightforward enterprise. All you have to do is go to Data, and then there's a command for this. It's called Text to Columns. And this opens up a Text to Columns wizard where Excel will walk you through how you want to do it. You can do fixed width or delimited. Fixed width is if the text fields have specific spaces between them. And this would actually probably work for MASTAN. But what I'm going to do is use the delimited option. And so when I hit Next, what Excel is looking for is it's saying, okay, your data is broken up by certain characters. What are those characters? Are they commas, semicolons, or maybe what they are are those vertical bars. So I'm using shift and the key above the enter, or the key above the enter key, and I'm going to say that the columns are split up by these vertical bars. So when I hit finish, boom, now it actually takes the data, as you can see, and now it's spit it out into individual cells, okay? Now it puts it in scientific notation. Sometimes that's a little difficult, at least for me, to visually see. So maybe what I'll do is highlight all of these and then go to the general tab, and instead of scientific, just make them general. And then do the same thing down here, even though we're not going to use this data, but you'll see why. Okay, so this is the data from our truss analysis. Now, one thing right off the bat that hopefully everybody sees that's accurate is that this is a truss analysis. So the only things that we should see are axial forces. So if you go down here, there's no moments in any of these members. That's accurate. That's correct. Okay. For the truss members, the only thing that we see is axial forces. Okay. But one thing that might be a little confusing is what's going on with, let's zoom into the data a little bit. Like, what does the data mean? Like, for example, you see element 1 and element 1, and there's 2 data points. In fact, for every element, there's 2 data points, and they're always equal and opposites. Like, for example, if I go to element 9, they're equal and opposite. So what's going on, and what does that mean? Okay, so what MASTAN is doing is it's reporting the forces at the end of each element. And so what happens is, because this is a truss element, the forces can only be one of 2 things. They can either be pointing this way, or they can be pointing this way. In other words, the element is either experiencing compression or it's experiencing tension. Now, an easy way of figuring out which is to remember that in MASTAN, we always consider forces to the right as positive. So the idea is, for each of these members, we just look at, so for example, element 1, you can see element 1 goes from node 1 to node 2. Element 4 goes from node 4 to node 5. Really, all you have to do is think about just an arbitrary element and look at the node on the right, the second node. If you have the node on the right, okay, and the force is going to the right, that means it's in tension. If the force is going to the left, that means it's in compression, okay? And so what does that mean here? Really, all you have to do is look at the second number for each element. And if it's positive, it's tension, okay? Because that force is pointing to the right away from the member. If it's negative, it's pointing toward the member. So element 1 is experiencing 420 kips in tension. Element 2 is experiencing 420 kips in tension. This one is 672, 672, 420, 420. This next one is negative 672. It's in compression. Okay, so all you have to do is use the second number, and it's pretty straightforward. If you go to the, if you go right here, you look at the analysis. I mean, that's how you can get this data. And the beauty of this is you only have to run the MASTAN model once to do this. That's all you got to do. Okay. The other thing that's worth mentioning is that because we're computing deflections, you're going to have to do a real analysis and a virtual analysis. The virtual analysis you can do in MASTAN2. Okay. So for example, let me cancel all this. All you have to do is just, here's the real model, maybe save this and then make a copy of it and call it a virtual analysis. And so what we'll do is we'll open the virtual model. And it's the same structure, just instead of all those 168 kip loads, we just have a virtual load of 1 right there. So run the real analysis, run the virtual analysis, and there you go. Okay. All right. So let me show you another trick. Okay. So that's one trick. I'm going to show you another trick, and then you'll see how I've combined that together in my calculations. Okay. So let me close this. I won't need this for our demonstration here. I want to refer everybody to this. Okay. If you recall, we were using this data to select a member. So what we would do is we would say, okay, let's take the, here, let me go back to that part here in the presentation. All right, so what we would do is we would say, let's go back to our analysis. And let's go back to how we would select a truss member. We would say we were limiting to W12s and that our stresses were limited to 36 KSI. So what we would say is that the we would calculate a required area as the load divided by sigma. We would say, okay, let's take a given member. The member has 672 kips. We would divide that by 36 KSI, get an area, and then pick a member that works, and we would get a W12 by 65. And then we would just do that for every member in the truss. Okay. And keep in mind that once we've selected members, we're going to compute deflections. We computed the deflections. We found that those deflections were too high, and so we had to iterate. We had to start changing members. So doing that in MASTAN would be an absolute pain. Doing it in Excel would be very easy if you know how to use table references and VLOOKUP. Okay, so let me show you a quick little trick. Okay, so by the way, here's the data that we were using to select truss members, and I also gave this to you via Excel. If you recall, I gave you this data in Excel. So this Excel sheet that I gave you, which is posted to Blackboard, is basically all the data for the W12s. So let me show you how this would work. Let me open up another fresh Excel sheet. Okay. Let me show you how this would work. So what I'm going to do is I'm going to copy the only data that I need for my project, which is this. Okay. I need, and I'll just call this on a shape, doesn't really matter. All I need is the shape, I need the area, and I am going to need the weight for each shape. This column here in the middle, I don't even need that. So I don't need that. Okay. So I don't want to have to type in areas over and over again, and I'd like a really easy way to start picking members. Okay. So one of the ways that we can do that is to use what's called data validation and to use what's called VLOOKUP. So let's start with the data validation first. So I'm going to maybe make a column right here called design and a column right here called area. And we'll just, we'll do a bunch of these and you'll see where this is going. Okay, so one of the things I want to be able to do is I want to be able to quickly pick members from this table over here. So I'm going to go into this design column and I'm going to go to the data tab and I'm going to go right here where it says data validation, and I'm going to click data validation. And I get this little window here. And what this is basically doing is it's telling Excel I only want the content of this cell to adhere to certain parameters. And what I want is I want the only thing that can go into these cells to come from a list. And what is that list? This. So I'll do that, hit OK. And if you notice, I get a nice little drop down box right here. And what I can do is actually now pick members. So the only thing that I'm allowed to do is pick different sections. Okay, I can have it blank, but you know, I can do that. Now, what do I want to do with that? Okay, so let's pick a section. Let's pick, I don't know, W12 by 120. Okay, so that's great, but I want to be able to use that. And the best command for that is what's called VLOOKUP. Okay, so the way VLOOKUP works is it says, okay, I want to find this value in this table. Okay, and if I find this value in this table, comma, I want to report something. Okay, now what does it report? What it's looking for is it says, okay, I'm going to look for this value in this table and I'm going to report whatever is in what column that you specify. So column 1 would be the shape column, column 2 would be the W column, column 3 would be the area column. So it goes 1, 2, 3. And then the last thing that you do is you put in false, because what we're looking for is an exact match, not an approximate match. We hit enter and boom. And so now what it did is it said, okay, I'm looking for the W12 by 120. I found it. And now that's the area. So what happens if I change this to a W12 by 58? it finds the appropriate area. What happens if I change my design to a W12 by 136? It finds the appropriate area, okay? So, and the cool thing is what you can do is if you go into your VLOOKUP command and make sure that you hit F4 and lock the cell reference for the table, you can go in and copy. We can say, okay, this member needs to be a W12 by 1 or 252. This member needs to be a W12 by 170. This member needs to be a W12 by 190. And it's changing the designs. Okay, so this is a really, really nifty trick. Okay, so if I take report generation in MASTAN and this in Excel and put it all together, what do I get? Okay, what I get is this. I'm gonna close all this, close all this. I get this. Okay. All right. So what I've done here in this spreadsheet, and I whipped this together in 20 minutes, you know, right before this recording this lecture, is I put all the Excel data right here, and I put a series of tables together. Okay, so what did I put here for these tables? Okay, so what I have here is all of my bottom chords. For example, my MASTAN model, this was the MASTAN model, and it had 21 members, right? So for each of these members, I reported a little f, a big F, and an L, right? So the little f came from the virtual analysis, the big F came from the real analysis. And where does this data come from? It just comes from the reports in MASTAN just generated, okay? Now what about L? Well, keep in mind that if you go to MASTAN, what you can do is you can say File, Create Report, and we'll clear all this text. Just give me a report on the geometry delimited by bars, and it'll tell you how long each member is. You don't need to calculate that. Just put that in, okay? And then I've got the E value. Now, again, the cool part, again, what I can do, here's this design column. What's the deal with this design column? The deal is that as I change members, it will change the area and it will change the weight later, okay? So now if you recall when I first ran the model, I just ran W12 by 14s. W12 by 14s are way too small for this. It certainly doesn't meet the stress limit and it certainly doesn't meet the deflection limit. But keep in mind, we're calculating deflections in Excel no differently than MASTAN is. So if we check MASTAN, we should be getting the same answer. Let me go back to my MASTAN model. Let's open up the real model again. Open up the real model. Oh, I didn't save it, so I need to attach those sections again. So let's define a section. Let's define the W12 by 14s. There we go. Let's attach those sections to the whole model. And then let's run the model. Now again, I'm running the real model with the real forces. Okay. Now, what am I getting in Excel when I calculate the deflections? I'm getting 7.976. Okay. So if I go to results and node displacements, what do I get here? 7.976. That should work. Okay. Because we're computing the deflections in MASTAN using the same theory, essentially the same mechanics that we're using in Excel. So that should match, okay? So there we go. So now what I can do is I can set up a column for stresses and set up a column for deflections. So one of the things I'm doing for the stresses is I'm saying, okay, here's the area. So, and again, I'm looking the area up. So what is the stress, okay? The stress, if I were to use this section, is the big F divided by the A. I get this. This is my sigma allowable. I put myself a little if-then statement in. You don't have to be that fancy. But essentially what I'm saying is if the member's stress is bigger than the 36 KSI, that member is no good. So any member that's blank, that's fine. But any member that's no good needs to be redesigned. Okay. And I'm going to have to start changing members up a little bit. So like, for example, if I go to this first member, I go, okay, that's too small. Maybe I need to make it a W26. Maybe I need to make it a W30. 35. Oh, W12 by 40, that works. Maybe what about the W12 by 35? The W12 by 35 is too small. The W12 by 40 works, okay? So maybe the first thing I'll do is I'll size all of my members to where they meet all the stress limits. And so if you do that, I went ahead and did that right before this. I got these are the members. They certainly meet, oh, sorry, wrong one. Sorry, let's do this one. These are the ones that meet all of the stress limits. But so you can see if I take any one of these members and I make them one size smaller, it's no good. So these are the bare minimum to meet the stress limits, but the problem is it's deflecting too much, because if you calculate deflections, and again, I'm just doing little f big F L over EA, if I calculate the deflections, it's deflecting too much. And if you recall, what I would do is increase the size of the member that has the biggest energy. And so I did another little if-then statement to help me out. I said, if this is bigger, if that member is the one with the biggest energy, check it. So maybe, here's this one I'll check. What I'll do is I'll up this member size a little bit. Maybe I'll up this member size a little bit. And I'll just keep doing that until I get a deflection that is under 2 inches. And so maybe we'll increase this one again. Increase that again. That isn't working, but you can see the deflection's getting smaller. And so you do a lot of work. Unfortunately, you do have to do a lot of work to get everything set up. But once you get it set up, you just go through and iterate until you find a member that works. And you keep doing this until you ultimately get to this design. And yeah, it still says you need to check those two, but the deflection's less than 2 inches, you're hunky-dory. And then just compute the price. And there you go. If you check my presentation, my price is a little bit slightly different than what you get in the presentation, but I wasn't doing the analysis via MASTAN. I was actually using like the square root of 2 as opposed to, for example, it rounding it off. Like, for example, if you look at these terms, those terms are basically square root of 2 over 2, but this is rounding it off every so far. So there's just a couple of Excel tricks just to make your life a little easier on the calculation side of things. But I want to make sure that we are going back in this example to our beam analysis. I'm going to close all this. Yes, I want to quit. Okay, let me close all this. Close all this. And let's go back to our focused lecture for today. This is what the other thing I wanted to talk about today is going back and doing other things with MASTAN. So keep in mind that when we use MASTAN, we are basically starting at geometry, working our way across, and when that's all said and done, we'll have fully defined a model from start to finish. And today what we're going to do is sort of cover everything that we didn't cover in our last lecture to basically fully finish out 2D linear elastic analysis. So there's 4 things I want to look at. I want to look at a beam with an internal hinge. I want to look at custom section creation. I want to look at different boundary conditions, including and also different loads like applied moments. And I want to look at uniformly distributed loads. The model that we're going to analyze is this model right here. We're going to consider this beam, and we're going to see if we can do a full-blown analysis. We're going to see if we can plot shear and moment diagrams and what have you. One thing I'll point out before we actually start chugging this out in MASTAN is that this beam has an internal hinge. And if you look there at the bottom, I sort of put the analytical model that we're going to use in MASTAN. And if you see here at node 2, there's this little green circle. I put it here as a green circle here in the presentation. You'll see how that plays into our model in MASTAN here in a bit. So what I did is, so that we would have something to reference, I sort of have this little image here that I'll keep open on the screen. Let's open up MASTAN and let's see if we can build this. I think you'll find that this is a pretty straightforward exercise. It's not very difficult. And I'm also going to maybe purposefully make a couple of mistakes in my model to show you that if you make those mistakes, what can you do about them? As we were doing this in class last time, I noticed there were a couple students who had some mistakes in their calculations. I thought maybe we'll see if we can fix those on the fly. So I'm actually going to start with those mistakes right now. So the first thing that we're going to do, let me make this window a little smaller so we can actually see the Let's see if we can see the beam as we're defining it. Let's do 0, 0, 0. And let's go, so we're going to create 4 nodes, and they're going to be along the x-axis. So we'll say 16, 32, and 48. And right off the bat, I've made a mistake. And the mistake is that if we're going to model in a consistent unit system, I needed to define those nodal coordinates in inches, not feet. And I define them in feet. So what do? Okay, I could delete the nodes or delete the model and start all over again. Or what I could do is see if I could scale the nodes. So one thing you can do is go to geometry and do scale nodes. And for example, what we'll do is select all the nodes, and we'll do them at a scale factor of 12 in the x-axis. We don't really need to worry about y and z because it's all 0. They're all the y and z coordinates are 0. But we'll say apply. And doesn't look like anything changed, but if you go to geometry and information on the node, you can see that the coordinates there at the bottom are now exactly what they should be. If you look at the handout for this this lecture. Okay, so again, mistakes are okay. You can account for them in MASTAN, and even if it's easier to just completely start the model from scratch, it doesn't take a long time to build these models, so it's not that big of a deal. Okay, so now we're going to create our elements. Our elements are pretty straightforward. Node 1 to node 2, node 2 to node 3, node 3 to node 4. Okay. Now our model is essentially done except for one issue, and that's the internal hinge. Okay, the internal hinge right here at node 2 needs to be handled. There's 2 ways of handling it, but a little background on that first. So the way that you model an internal hinge in MASTAN is what's through defining a connection. Okay, so if you go to geometry, you can define connections. You can either define a flexure connection or a torsion connection. A hinge is a flexure connection because it releases moment. So we're going to use a flexure connection. Now, the way that MASTAN handles this is it releases an element's ability to withstand, these forces on either end. So like I said, there were 2 ways of defining a hinge. One way that we could define a hinge is to release the moment on the right end of element 1 or the left end of element 2. Structurally, it really won't matter. You'll get the same structural response. It might affect the data that you are getting at the end, and maybe you're interested in different data, but it won't really affect how the structure responds. So I'm going to do the first one. I'm going to do the right end of element 1. So I'm going to click element 1, and I'm going to say, instead of node I, node J, I'm going to take node J and make it pinned. What it does, you can see that little circle that it put there. What it's saying is that end of the member, it's going to act like a hinge. Okay. Now, one thing you don't want to do is both. Don't put both don't release this one and this one because it can cause your model to be unstable. Just do one. Don't do both. Okay. All right. So now that our geometry is created, we can start defining some properties. So the first thing I'm going to do is define a section. Now, what we're going to do for this problem is we're going to create a custom beam. So we'll call the name, I don't know, custom 1. Now, in the last example, what we had done is gone to the database and picked one. We're not going to do that here. Let me cancel. Oh, let me cancel this. I shouldn't have clicked that. So what we're not going to do is click the database. What we're going to do is actually just type in some values. Now, which values do we type? Because it looks like there's a lot of stuff here. What do we need to do? Depending upon the complexity of your analysis, you may need to do all of these. But for a 2D beam analysis, you really need to only input 2 values. You have to input an area, but we're not going to need an area for this analysis. You would for a frame, but we're not going to need it. So I'm just going to put an area value of 1. Even though for a beam, it won't actually affect the results, MASTAN needs a number there. And then you need a moment of inertia. And the moment of inertia that you need to input is the moment of inertia about the z-axis, because the z-axis is sort of in and out of the screen, and that's sort of the axis about which the moments are applying. And for this problem, we're going to do a moment of inertia of 15,000. So we'll hit apply. There's our section. And then we'll go to properties, attach section. We'll just attach that to all members. And then we'll create a material. Sorry, property, or define material. We're going to call this material concrete. We'll just do a 4,000 here. These other values that you see here are more appropriate when you're doing a nonlinear analysis, like the Fy and whatnot. I mean, concrete doesn't have an Fy, but let me apply here. Concrete doesn't have an Fy, but you know, if you were doing a nonlinear analysis, some of these values would matter. Okay, so we'll attach the material, attach material to all members, apply. Okay. So now our geometry and our materials are fully defined. We can tell that because all of the elements are solid. And so now what we're going to do is start applying conditions. So we're going to apply some fixities. We have two boundary conditions at node 1. Node 1 is a fixed support, okay? So we're going to restrain it in the x direction, the y direction, and then the z rotation, because we have to apply a moment reaction as well. And the moments in 2D are about the z-axis. So we hit apply. Hit cancel. If you want to, in MASTAN, if you want to zoom in and out, or if you want to contain the whole screen, you hit Control F. So if you want to see all of your reactions, that might make that a little easier. But you can see I've got X, Y, and my moment reaction there. I also need another condition there at node 3. I need the Y displacement there. So those are my boundary conditions. You can see that up here. Now we need to start applying the loads. Okay, so what I'm going to do is I'm going to apply the, let's see, what do I want to apply first? Let's apply the forces first. So let's define a force. This has a nodal force of 40 kips there over here. So we'll put that as negative 40. Apply. And we also need to apply a moment, okay? And the way that works, we'll go to conditions, define a moment. We're going to put a moment right here as well. And we need to apply a moment. This is a clockwise moment of 200 foot kips. So clockwise is considered negative. So we're going to do negative 200, but that's 200 foot kips. Remember, our models are in inches and kips. So we need to multiply that times 12 to get that into inch kips. Okay. And then we'll hit apply. I'll hit Control F just to zoom everything in. So now we can see that moment is applied the way it's supposed to. All right, the only thing left to do before analysis is to apply this distributed load. So we're going to go to conditions. This is called a uniform load in MASTAN. So we're going to click this member and this member. What we have here is, so it's asking for WX, WY, and WZ. We're going to use WY because load's going down. And it is 0.9 kips per foot, so negative 0.9 divided by 12 to get that in kips per inch, and we'll hit apply. The only thing I'll say, and this doesn't really matter for any of the problems we're going to do in this class, but you'll see this input reference to local or global. I don't want to say much about that now other than to say when we start talking about matrix analysis at the very end of the semester, you'll have a better understanding of what local and global coordinates are, but that'll become relevant a little bit later is all I'll say. Okay, so we hit cancel, and our model is ready to go. It's loaded, fixed, all the section properties are applied, so we just go to analysis, static, first order elastic. Make sure it says planar frame. Some of you might be thinking that, well, wait, there's a truss and a frame, but there's no beam. Beams and frames are handled basically the same in MASTAN. So, because same, what we'll call stiffness matrix. We'll talk about that later, but it's the same stiffness matrix essentially. That stiffness matrix has an A value in it, which is why you have to put an A value in MASTAN, even though the A value won't affect this type of analysis. Again, we'll talk about all that later. So we hit apply. And there we go. Our model is created and run. So now the only thing left to do is to start querying some data. So a couple things that we can do. and maybe we'll get a little bit fancy with this. First thing I'll do, let's just make sure we're comfortable with the deflected shape, so we can go to results. Let's do a deflected shape. We'll just hit apply. I'm just doing that at a scale factor of 10 so we can see the structure deforming. And again, if we wanted to animate that, we could. I'm not going to worry about that here, but we could animate it if we would like. What I'm going to do now, let me cancel this. Let's turn that off. Okay, there we go. What I'd like to do, if this is a beam analysis, I'd like to see the shear diagram and the moment diagram. But the way MASTAN's going to do this is if I plot it now, it's just going to plot it on top of everything, just like it did with the deflected shape. And that might get a little crowded, and I'd kind of actually, like to see what's going on. So I'm going to go to View, and I'm going to start turning some things off, okay? Let's see. Let's go to View, and let's go to Labels, and let's see if we can start turning some things off. So, for example, if I go to View Node Numbers, View Labels, Element Numbers, View Labels, Loads, View Labels, Fixities. So everything's there. It's just turning the display of them off, almost sort of like turning a layer off in AutoCAD. So now let's look at results. Now let's look at some diagrams. And what I'm going to do is I'm going to do a shear force diagram. So let's see. Let's just hit apply. And boom, now we have a shear force diagram. And that sort of looks exactly like we would expect. So what MASTAN is doing is it's reporting the shears at the end of each element. So for example, at joint or node 2, you can see it's sort of doing a 45.3 twice because at the end of each element, you're getting the same shear force there. You can see the jump in shear, and you can see that right there. And if you look at the beam right here, I mean, it should be a linear shear diagram and then a constant shear diagram from here to here because there's no loads there. So that would make sense. The other thing we can do, for example, we can go to results diagrams. Let's do a moment diagram. Let's do a moment. We got to do moment Z. So we'll hit apply. And let's do this. Let's fill it. Give it some color. Okay. And then here's our moment diagram. And you can see that moment diagram is that what we would expect? Well, it's kind of hard to see right now. Maybe what I'll do is maybe I can, maybe what I can do is zoom out. So I'm using Control Z and I'm zooming out a little bit. What I'm trying to do is maybe try and show that this is non-linear. You can see it's kind of curved. It's maybe a little hard to see here, but it is indeed curved. This is a straight line segment, and then we get a sudden jump right here. And look what it's reporting here at negative 2400 and then a jump up to 0. Where's the negative 2400 come from? It's the 200 foot kips, 200 times 12. Now, why are like I say, why are the numbers so large? Because it's in inch kips, not foot kips. So again, consistent unit system across the board. Okay, well, I hope that clears up and makes MASTAN a pretty straightforward enterprise. You all have a homework assignment due Wednesday on 2 problems in MASTAN, and so I just want to sort of just a neatly detailed report. You can do it in Word, and again, you can always, for example, we could say File, Print Photo to PNG, and we can put this. We'll put this on the desktop. We'll call it, I don't know, moment diagram. And now you can see we have a moment diagram image right here that we can very easily just put in an Excel in a Word document for a report. So there should be no reason you can't create a really neat report for this submission. Okay, and with that, that's all I have, everybody, and I will see you on Wednesday.